Welcome to this session of Advanced Calculus. In this unit, we will discuss chain rule of differentiability and mean value theorems. Chain rule of differentiability. In 17th century, the world of science and mathematics had experienced significant developments, and amongst the greatest of these were the differential and integral calculus. Calculus was developed independently by the English mathematician Sir Isaac Newton and by the German Gottfried Leibniz. The differential calculus is an indispensable tool in every branch of science and engineering where we study the comparison of quantities that vary in a nonlinear way. The derivative of a function is a measure of how the function changes as its input changes. Now, we give the formal definition of derivative of a function which uses the concept of limit. Definition. Let f from closed interval a b to r be a real valued function defined on an interval a to b subset of r. The function f is said to be differentiable at a point c element of open interval a b if limit x tends to c f of x minus f of c by x minus c exists. The value of this limit, if x is called the derivative of f of x at the point c, and it is denoted by f prime of c. The function f is said to be differentiable at the left-hand point a if f prime of a plus equal to limit x tends to a plus f of x minus f of a by x minus a exists. The function f is said to be differentiable at the right-hand point b if f prime of b minus equal to limit x tends to b minus f of x minus f of b by x minus b exists. The function f is said to be differentiable on closed interval a b if it is differentiable at each point of closed interval a b. Remark: the derivative of f of x is obtained by looking at the changes of input values x. So, the value f prime of c is the derivative of function f with respect to a variable x at the point c. This can also be represented by the denotation df by dx given by Leibniz. The process of finding a derivative is called differentiation. Now let us consider one of the necessary conditions for a function to be differentiable. Theorem. Let f be a real valued function defined on an interval I. If the function f is differentiable at c in I, there exists a function lambda on I that is continuous at c such that f of x minus f of c equal to x minus c into f prime of c plus lambda x and limit x tends to c lambda of x equal to 0. Proof. Given that f prime of c exists, so f prime of c equal to limit x tends to c f of x minus f of c by x minus c. Define function lambda on I by lambda of x equal to f of x minus f of c by x minus c minus f prime of c if x not equal to c, lambda of x equal to 0 if x equal to c. Then limit x tends to c lambda of x equal to limit x tends to c of f of x minus f of c by x minus c minus f prime of c, which is equal to limit x tends to c of f of x minus f of c by x minus c minus f prime of c, which is equal to f prime of c minus f prime of c equal to 0. Therefore, limit x tends to c lambda x equal to lambda of c. This shows the continuity of function lambda at c. Now, by definition of lambda, for x not equal to c, f of x minus f of c by x minus c equal to f prime of c plus lambda of x. Thus, f of x minus f of c equal to x minus c into f prime of c plus lambda of x. If x equal to c, then both sides of the above equation equal 0. Hence, the theorem is proved. Now, we establish a relation between differentiability and continuity. Theorem. If f from I to r has a derivative at c element of I, then f is continuous at c. Proof. Given that the function f has derivative at c element of I, therefore, f prime of c equal to limit x tends to c f of x minus f of c by x minus c exists. Now, for all x element of I, x not equal to c, we have f of x minus f of c equal to f of x minus f of c by x minus c whole into x minus c. Taking limit as x tends to c and applying product rule for limits, we get limit x tends to c f of x minus f of c equal to limit x tends to c f of x minus f of c by x minus c into limit x tends to c x minus c, which is equal to f prime of c into 0, which is equal to 0. This shows that limit x tends to c f of x equal to f of c. Hence, f is continuous at c. Note: the converse statement of the above theorem need not be true. That is, the continuity of a function at a point does not assure the existence of derivative at that point. Early in the history of calculus, many mathematicians assumed that a continuous function was differentiable at most points. In 1872, Carl V. Strauss found the first example of a function that is continuous everywhere but differentiable nowhere. Let us see an example. Let f from closed interval minus 1 to 1 to r be defined by f of x equal to absolute value of x. Here f of 0 equal to 0. Limit x tends to 0 plus f of x equal to limit h tends to 0 f of 0 plus h, which is equal to limit h tends to 0 absolute value of h, which is equal to 0. Limit x tends to 0 minus f of x equal to limit h tends to 0 f of 0 minus h, which is equal to limit h tends to 0 absolute minus h equal to 0. Therefore, limit x tends to 0 f of x equal to f of 0. So, the function f is continuous at x equal to 0. Now, f of x minus f of 0 by x minus 0 equal to absolute value of x minus 0 by x, which is equal to absolute x by x, which is equal to 1 if x greater than 0 equal to minus 1 if x less than 0. If we take the limit of this difference quotient as x approaches 0 from left and right, the values are minus 1 and 1 respectively. Thus, limit x tends to 0 f of x minus f of 0 by x minus 0 does not exist. So, the function f does not have derivative at x equal to 0. Hence, it follows that every continuous function may not be differentiable. There are a number of simple rules which can be used in the calculation of derivatives of various combinations of functions. The following theorem states some of them. Theorem: let f and g be real valued functions defined on an interval I equal to closed interval ab and be differentiable at a point c in I. Then 1. Constant multiple rule. Kf is differentiable at c for constant k and kf prime of c equal to k into f prime of c. 2. Sum rule. F plus g is differentiable at c and f plus g prime of c equal to f prime of c plus g prime of c. 3. Difference rule. F minus g is differentiable at c and f minus g prime of c equal to f prime of c minus g prime of c. 4. Product rule. Fg is differentiable at c and fg prime of c equal to f prime of c into g of c plus f of c into g prime of c. 5. Quotient rule. If g of c not equal to 0, f by g is differentiable and f by g prime of c equal to f prime of c into g of c minus f of c into g prime of c by g of c whole square. We now turn to an important rule of differentiation, namely the chain rule. Let us consider a real valued function f of x equal to x cube plus 5 whole raised to 25. To find the derivative of this function using rules stated so far, we have to expand x cube plus 5 whole raised to 25 and differentiate. Consider the diagram. X goes to x cube plus 5, then goes to x cube plus 5 raised to 25, a function followed by another function. That is, x goes to x cube plus 5 under a function h and x cube plus 5 goes to x cube plus 5 raised to 25 under another function g. So, the function f of x is considered as the composition of two functions g of t equal to t raised to 25 and h of x equal to x cube plus 5. Can we follow this chain to find the derivative? This is what the chain rule says. In calculus, the chain rule is a formula for computing the derivatives of composition of two or more functions. This rule seems to have first been used by Leibniz. However, he did not state it as a separate rule, nor did anyone else for a long time. L'Hopital used the chain rule implicitly, but he did not state it explicitly. The first explicit and modern statement of the chain rule was given by Lagrange in 1797. Chain rule. Let I, J be intervals in capital R, F from I to R and G from J to R be functions such that f of I subset of J and let C element of I. If f is differentiable at C and if G is differentiable at f of C, then the composite function G composite f is differentiable at C and G composite f prime of C equal to G prime of f of C into f prime of C. Proof. Since f is differentiable at C, there exists a function lambda on I such that f of x minus f of C equal to x minus C into f prime of C plus lambda x, where lambda x tends to 0 as x tends to C. Again, since G is differentiable at f of C, there exists a function mu on J such that g of y minus g of f of C equal to y minus f of C into g prime of f of C plus mu of y, where mu of y tends to 0 as y tends to f of C. Substitution of y equal to f of x shows that g of f of x minus g of f of C equal to f of x minus f of C whole into g prime of f of C plus mu f of x for all x element of I. So it follows that g of f of x minus g of f of C equal to x minus C into f prime of C plus lambda of x whole into g prime of f of C plus mu of f of x for all x element of I. Therefore, g of f of x minus g of f of C by x minus C equal to g prime of f of C plus mu f of x whole into f prime of C plus lambda of x. Since f is differentiable at C, it is continuous at C and so f of x tends to f of C as x tends to C. As a consequence, it follows that lambda of x tends to 0 and mu of f of x tends to 0 as x tends to C. Thus, taking limit as x tends to C, we have limit x tends to C g of f of x minus g of f of C by x minus C equal to g prime of f of C into f dash of C, and the proof is completed. Many of the differentiation problems need the chain rule. It sometimes helps to think about it the following way. 1. To differentiate composite g of f of x at C, consider g as the outside function and f as the inside. The derivative of g composite f is the derivative of outside function g keeping inside function as a variable and then multiply it by the derivative of the inside function. 2. To differentiate composite g composite f, consider the chain as in the following figure. Then the derivative of g composite f at C is the product of derivatives of f and g. This will be helpful in the case of composite of 3 or more functions. 3. If f is a differentiable function of u and u is a differentiable function of x, then chain rule formula in D notation takes the form df by dx equal to df by du into du by dx. This can be extended to a finite number of functions as df by dx equal to df by dw into dw by du into du by dx. Let us work out some differentiation problems using chain rule and standard results. Example. Let y equal to root of x square plus 1. Take u equal to x square plus 1. Then y equal to root u. By chain rule, dy by dx equal to dy by du into du by dx is equal to 1 by 2 root u into 2x equal to x by root of x square plus 1. Example. Let g of t equal to tan phi minus sin 2t. We consider this as the composite of t goes to 2t, then goes to sin 2t, then goes to phi minus sin 2t, then goes to tan of phi minus sin 2t. The derivative is obtained by following the chain as g prime of t equal to 2 into cos 2t into 0 minus 1 into secant square phi minus sin 2t, which is equal to minus 2 cos 2t secant square phi minus sin 2t. Example. Let y equal to 1 plus tan raised to 4 of t by 12 whole raised to 3. Then dy by dt equal to 3 into 1 plus tan raised to 4 t by 12 whole square into d by dt of 1 plus tan raised to 4 of t by 12, which is equal to 3 into 1 plus tan raised to 4 t by 12 square into 0 plus 4 tan raised to 3 of t by 12 into d by dt of tan t by 12 equal to 3 into 1 plus tan raised to 4 t by 12 whole square into 0 plus 4 into tan raised to 3 of t by 12 into secant square t by 12 into d by dt of t by 12, which is equal to 3 into 1 plus tan raised to 4 t by 12 whole square into 4 tan raised to 3 of t by 12 into secant square t by 12 into 1 by 12 equal to 1 plus tan raised to 4 t by 12 whole square tan raised to 3 t by 12 secant square t by 12. Mean value theorems. Mean value theorem is one of the most important theoretical tools in calculus. It relates the values of a function to values of its derivatives. Let f of x be a real valued continuous function defined on the closed interval a to b. We look at the graph of the function. Take 2 points capital A and capital B on the graph as in the figure 1. Then we can see that there exists a tangent line parallel to the line AB. In other words, there is a point on the curve such that the tangent line at that point has the same slope as the line AB. This intuitive idea is the essence of mean value theorem. The modern generalized form of mean value theorem was stated by Augustin Louis Cauchy. Before we get to the mean value theorem, we need to prove the following. Rolle's theorem. Suppose that f is a real valued function that is continuous on closed interval a to b, differentiable on open interval a to b, and f of a equal to f of b equal to 0. Then there exists at least one point c in open interval a to b such that f prime of c equal to 0. Proof. If f of x equal to 0 for all x in closed interval a to b, then any c in open interval a b will satisfy the conclusion of the theorem. Suppose f does not vanish identically. Since f is continuous on closed and bounded interval a to b, it attains its bounds small m equal to infimum of f of x such that x element of closed interval a to b and capital M equal to supremum of f of x such that x element of closed interval a to b. Then at least one of small m and capital M is non-zero. Let capital M not equal to 0. So there exists c in closed interval a to b such that f of c equal to m not equal to 0. But f of a equal to f of b equal to 0. Now f of c not equal to f of a, f of c not equal to f of b imply that c not equal to a, c not equal to b, and so c is in open interval a to b. Since f is differentiable in open interval a to b, f prime of c equal to limit x tends to c f of x minus f of c by x minus c exists. Thus, for each epsilon greater than 0, there exists delta greater than 0 such that absolute value of f of x minus f of c by x minus c minus f prime of c less than epsilon whenever 0 less than absolute value of x minus c less than delta. Therefore, f prime of c minus epsilon less than f of x minus f of c by x minus c less than f prime of c plus epsilon for all x element of capital V equal to open interval c minus delta to c plus delta and x not equal to c. Case 1. If f prime of c greater than 0, choose epsilon such that 0 less than epsilon less than f prime of c. Then 0 less than f of x minus f of c by x minus c for all x element of capital V and x not equal to c. Therefore, for any x element of V and x greater than c, we have f of x minus f of c greater than 0. Case 2. If f prime of c less than 0, choose epsilon greater than 0 such that epsilon less than absolute value of f prime of c. Then f of x minus f of c by x minus c less than f prime of c plus absolute value of f prime of c for all x element of V and x not equal to c. This shows that f of x minus f of c by x minus c less than 0 for all x element of capital V and x not equal to c. Thus, for any x element of V and x less than c, we have f of x minus f of c greater than 0. Therefore, in both cases, there exists x element of V subset of closed interval a to b such that f of x minus f of c greater than 0. This contradicts the fact that f has maximum at c, so we must have f prime of c equal to 0. This proves the Rolle's theorem. Corollary to Rolle's theorem. Suppose that f is a real valued function that is continuous on closed interval a to b, differentiable on open interval a to b, and f of a equal to f of b. Then there exists at least one point c in open interval ab such that f prime of c equal to 0. Proof. Let f of a equal to f of b equal to k. Define a function g from closed interval a to b to r by g of x equal to f of x minus k for all x in closed interval a to b. Then g is continuous on closed interval a to b, differentiable on open interval a to b, and g prime of x equal to f prime of x. Now g of a equal to f of a minus k equal to 0 and g of b equal to f of b minus k equal to 0. Thus the hypotheses of Rolle's theorem are satisfied by g, and hence there is at least one point c in open interval ab such that g prime of c equal to 0, that is f prime of c equal to 0. This proves the corollary. As an application of Rolle's theorem, let us see the following example which deals with the distinct roots of an equation. Example. Consider an equation x square minus 3x plus k equal to 0. Assume that there exists a real number k for which the given equation has two distinct roots alpha and beta in closed interval minus 1 to 1 with alpha less than beta. Now consider the closed interval alpha to beta subset of closed interval minus 1 to 1 and define f of x equal to x square minus 3x plus k for all x in closed interval alpha to beta. Then f, being a polynomial, is continuous on closed interval alpha to beta, differentiable on open interval alpha to beta, and f prime of x equal to 2x minus 3. Since alpha and beta are roots, f of alpha equal to 0 and f of beta equal to 0. Thus, by Rolle's theorem, there exists at least one c in open interval alpha to beta such that f prime of c equal to 0. This shows that 2c minus 3 equal to 0 and c equal to 3 by 2. But we can see that 3 by 2 does not belong to closed interval minus 1 to 1, and so c not element of open interval alpha to beta. This contradicts the conclusion of Rolle's theorem. Thus, it follows that there exists no real number k for which the given equation has two distinct roots in closed interval minus 1 to 1. Mean value theorem. If f is a real valued function that is continuous on closed interval a to b, differentiable on open interval a to b, then there exists at least one point c in open interval a to b such that f of b minus f of a equal to f prime of c into b minus a. Proof. Consider the function phi defined on closed interval a to b by phi of x equal to f of x minus f of a minus f of b minus f of a by b minus a into x minus a for all x in closed interval a to b. Since f is continuous and differentiable, phi is continuous on closed interval a to b and differentiable on open interval a to b, and phi prime of x equal to f prime of x minus f of b minus f of a by b minus a. Moreover, phi of a equal to f of a minus f of a minus f of b minus f of a by b minus a into a minus a, which is equal to 0, and phi of b equal to f of b minus f of a minus f of b minus f of a by b minus a into b minus a, which is equal to 0. So, the hypotheses of Rolle's theorem are satisfied by the function phi. Thus, there exists at least one c in open interval a to b such that phi prime of c equal to 0, that is f prime of c minus f of b minus f of a by b minus a equal to 0. Therefore, there is at least one c in open interval a to b such that f of b minus f of a equal to f prime of c into b minus a. This proves the mean value theorem. Geometrical interpretation of mean value theorem. Let f of x be a real continuous function on closed interval a to b, differentiable on open interval a to b. Let capital A and capital B be 2 points on graph of the function corresponding to x equal to a and x equal to b respectively. Then coordinates of these points are a f of a and b f of b. slope of the line segment capital AB equal to difference of y coordinates by difference of x coordinates, which is equal to f of b minus f of a by b minus a. By mean value theorem, this quantity is f prime of c for at least one c between a and b. But f prime of c is the slope of the tangent to the curve at c. Hence, slope of AB equal to slope of the tangent to the curve between a and b. Thus, geometrically, mean value theorem says that somewhere between capital A and capital B, the curve has at least one tangent parallel to the chord AB. The mean value theorem can be used to draw conclusion about the nature of function from its derivative. The following results are obtained in this manner. Theorem: if f from AB to R is continuous on closed interval a to b and differentiable on open interval a to b, and f prime of x equal to 0 for all x in open interval a to b, then f is a constant function. Proof: let x1 and x2 be any two points in closed interval a to b with x1 less than x2. The hypotheses of mean value theorem are satisfied by f of x on the closed interval x1 to x2 subset of closed interval a to b. So, there exists at least one c in between x1 and x2 such that f of x2 minus f of x1 equal to f prime of c into x2 minus x1. Given that f prime of x equal to 0 for all x in the open interval a to b, therefore f of x2 minus f of x1 equal to 0. Thus, it follows that f of x1 equal to f of x2 for any two x1 and x2 in the closed interval a to b. Hence, f is a constant function. Corollary: real valued continuous functions defined on a closed interval with the same derivatives differ by a constant. Proof: let f from ab to r and g from ab to r be two continuous functions such that f prime of x equal to g prime of x for all x in the open interval a to b. Define a function h from closed interval ab to r by h of x equal to f of x minus g of x for all x in closed interval a to b. Then h prime of x equal to f prime of x minus g prime of x equal to 0 for all x in the open interval a to b. So, by previous theorem, h is a constant function. Thus, there exists a constant c such that f of x minus g of x equal to c. Therefore, f of x equal to g of x plus c for all x in the closed interval a to b. This proves the corollary. Generalized mean value theorem: if f and g are continuous real functions on closed interval a to b which are differentiable on open interval a to b, then there exists c in open interval a to b such that f of b minus f of a into g prime of c equal to g of b minus g of a into f prime of c. Proof: define function h from closed interval ab to r by h of x equal to f of b minus f of a into g of x minus g of b minus g of a into f of x for all x in closed interval a to b. Then, by the continuity and differentiability of f and g, it follows that h is continuous on closed interval a to b, h is differentiable on open interval a to b, and h prime of x equal to f of b minus f of a into g prime of x minus g of b minus g of a into f prime of x. Now, h of a equal to f of b minus f of a into g of a minus g of b minus g of a into f of a equal to f of b into g of a minus g of b into f of a, and h of b equal to f of b minus f of a into g of b minus g of b minus g of a into f of b, which is equal to g of a into f of b minus f of a into g of b. Therefore, h of a equal to h of b, and by corollary to Rolle's theorem, there exists one c in open interval a to b such that h prime of c equal to 0. Hence, f of b minus f of a into g prime of c equal to g of b minus g of a into f prime of c. This proves the theorem. Example: if f of x equal to x minus 1 into x minus 3 into x minus 5 is a function defined on closed interval 0 to 4, find the value of c such that f prime of c equals the slope of the chord joining the points for which x equal to 0 and x equal to 4. Solution: Since f of x equal to x minus 1 into x minus 3 into x minus 5 is a polynomial, it is continuous and differentiable. By mean value theorem applied to the continuous function f of x on the closed interval 0 to 4, the slope of the chord f of 4 minus f of 0 by 4 minus 0 equal to f prime of c for some c in between 0 and 4. Here f of 4 equal to 4 minus 1 into 4 minus 3 into 4 minus 5, which is equal to minus 3. F of 0 equal to 0 minus 1 into 0 minus 3 into 0 minus 5 equal to minus 15. F prime of x equal to x minus 3 into x minus 5 plus x minus 1 into x minus 5 plus x minus 1 into x minus 3, which is equal to 3x square minus 18x plus 23. Therefore, by mean value theorem, 3c square minus 18c plus 23 equal to 3 for some c element of open interval 0 to 4. This shows that c equal to 9 plus or minus root 21 by 3. But c lies in between 0 and 4. Hence, c equal to 9 minus root 21 by 3. In this unit, we have discussed chain rule for differentiability and mean value theorems.